Okay, good. So welcome, we have about 28 participants today, as we can see from the Zoom. So we'll get started in a minute or two. Okay, so that is going live to YouTube, so later on you can take a look at that. So just to be clear, because it is going on YouTube, your face might be recorded. So we do post-edit the YouTube videos down. So if there's a particular part which is not flattering to you, please let me know. We will be happy to edit it out, okay? But just to let you know and to set the ground rules, this session is a public session. It's meant for my research group here at NUS, as well as a number of 6101 PhD students who are in their first year doing lab rotations. But it is open to the public. So we have some people who are interested from the public who are welcome to join. And if you have friends or other group members from your particular research groups or labs that want to join, they are welcome to do so. You can add them yourself to the Slack group. The Slack is pretty open, so you can just let them come in, okay? But because this is an open group, I want to make it clear at the beginning, this is not a lecture, okay, not given by staff. This is the only way that NUS allows me to conduct this in the open. Otherwise, it would be closed and we'd have to charge tuition fees, okay? So it is not meant to be an actual lecture by NUS staff. So we're not teaching anything per se. This is a reading group, okay? So that said, I hope many of you will turn on your cameras so that everyone can have a chance to look around and to get to know each other a little bit. So I'm going to go through some administrative things first. And if you have any questions, let me know, okay? So, all right, so let's get started. So because when I go full screen on these things, I can't see notifications, so we're just going to leave it on the Google Slides, just in the slide sorter mode. Okay, so just to be clear about this, if you have come into this session, you should be part of the Slack group. You can go to 6101.slack.com to join that group if you haven't already. And there is a pin post. I'm going to pull up that part here. You see? Okay, so there is a pin post here. Okay, which I'm going to just put it up. All right, which describes how the reading group works. All right, so basically there are a couple different assignments. Okay, this is just to make the reading group work well. Okay, we have a group of students every week who are going to be assigned the lecturer role. Okay, this is a sort of a misleading name because it doesn't mean that they have all the answers to the materials that they're sharing. Like I said, this is a reading group. It's a little bit basic or intermediate at most. It's not really advanced. So, for this reason, there will be some disfluencies and you might not get always the correct or accurate answers. The whole point is to have a dialogic discussion, okay, a discussion, not to get answers, okay? So hopefully through this involvement with you included, it will be easier to work with, okay? So, so basically my job is just to tell people to participate. Okay, I'm actually not going to lecture much. So if you see comments on some of the other videos, they'll say, why aren't you teaching? Well, this isn't a class, okay? And as a group of lecturers, the students who are assigned to do this, okay, so all of you would take turns in doing it, it's a good idea to check what you want to cover, okay? So when you're assigned as part of a lecturing team, there may be up to 5 people involved, okay? You can find tutorial slides or conference presentation slides on the web. And I encourage you to integrate those into your presentation. Just credit other people when you use them. Everyone loves to get citations and everyone likes to get praise from other groups that use your materials again. So write to them, tell them, hey, I'm using your material for a reading group over at NUS, and I really appreciate that you made these materials. and thank them for that. Okay, so if you do that, you can assemble a group of Google Slides as Tongyao and Zijin will present later on. Okay, and then basically just try to discuss. Okay, and again, because it is not a lecture, it is a discussion group. All right, it means that we want everyone to participate. If you're not participating either in the Slack channel or orally here in this, you're not getting your bang for the buck. Okay, well, that's a misnomer. I shouldn't say that because you're not paying anything for the course, except for NUS students who are paying through their scholarship and time. Okay, so because of that, we want to limit the amount of material that we want to cover. It's good to cover about 2 to 3 papers, okay, and to have lots of discussion. And you can take your discussion to Slack, or you can do it in here in the Slack channel, sorry, on the Zoom chat, but it's probably better to put it on the general channel. Okay, that's what we use it for. Okay, if there's lots of other material, especially you might direct it to the second half of the lecturing group, which is the support staff, which I'll talk about later on. Okay, so that other people can follow along. Okay, so I ask that most people who participate in this research group, you have your Zoom on one side of the monitor and your Slack on the other, or if you're lucky enough to have dual monitors, then by all means put them on both sides. Okay. Um, and try to help out each other during your presentation. So when you're assigned as a lecturer, you should be talking for the part of slides that you're happy to present. Okay, and again, no worries if you mess up or anything. We are all a very friendly group of people. We want it to be a dialogue. So if you have no clue about what the math on this slide says, you can just say, I have no idea what's going on. Can someone help me explain? Okay, and that is preferred behavior actually, because many times when we ask questions or we put up something we don't know, somebody else in the group can relay their understanding. And if it's incorrect, again, it's fine. Okay, the whole point is to have a dialogue. Okay. So that's why even though we put these videos on YouTube, they're not very useful. It's just a whole bunch of people trying to ruminate and think about things. It's really helpful to be here live, right? Because then you benefit from that. Okay. Many times you'll see papers, they report really great F1 scores or whatever metrics. Those are usually not too interesting to us unless they've done a lot of experimental analysis. When they do careful analysis about why the results are the way they are, then it's helpful to recap that so that we understand why does a particular model function a certain way to get rid of certain types of errors. Okay. And then ideally, when you are in charge of the reading group as a lecturer, for the week that you're in charge of, obviously we have our session on Friday. That means you want to list at least the key papers that you're trying to look at, the 2 or 3 ones that you think you're going to look at on Tuesday. It's okay if you're not quite right, you didn't find what you wanted to go over, or some other paper interests you more, then you can update that list. But this is just so that when we go into the reading group, people have a chance to at least download the papers and look at them. Okay, just as Tongyao and Zijin did. Okay. Now, as I said, there are 2 roles in this course. One is a lecturing staff, and the other one is support staff. Okay, support staff are basically people to help with the lecturing, because in this e-learning scenario and in general, we find that having another group of people helping to scribe, so somewhat like what the medical community does. If you're a medical student, you have to scribe the professor's lecture, right? So we're doing the same thing. Okay, so there will be a bunch of other people, and everyone will take turns in both of these roles, okay, to do this type of work where you actually have to scribe a document that basically summarizes what the lecturers went over. Okay, both your scribe notes and the lecturer's slides will be made public on the webpage. Okay, and to do a couple things. So one of the duties is to revisit the video of the lecture. Again, it's being casted to YouTube, so you can watch it again, and look at the comments in the general channel to try to compile all of those bits of information into the document itself, into the Scribe document itself. Okay, And then there's another set of duties, which is better handled by another student or another participant, okay? That is to update the actual documents, the public-facing documents that you may have seen that might have generated your awareness of this reading group, okay? So you do this, I assume everyone knows how to use Git. So it's a GitHub page. So you just issue a pull request on the repo, just check it to make sure it merges properly and it'll be integrated, okay? So you can add in the links to the YouTube video, which is already now public, and then information about the scribe notes and the list of papers, okay? I'll show you what that looks like in a minute or two. All right. Different scribes can be assigned different roles. So as I said, there are a couple different things that scribes do. It's just to make sure that everything after the fact is done well. Okay. All right. Okay. So with that, we also have these two particular roles, right? Lecturing role and a support slot. Okay. So PhD students in my group have to do 2 lecturing slots, one for the first half of the course and one for the second half of the course. And they need to play the support role once, okay? Everyone else, meaning external participants, 6101 students who are their first year PhD students doing lab rotation for this course have to do it once. Now, 6101 students, those of you who know that it's basically a lab rotation 2-credit module course in NUS for our first year students, they will need to do 1 lecturing slot that is aligned to the half of the semester that they're functioning for this course, okay? So in 6101, you can elect to be in the first half or the second half. I think we have a majority of people for the second half. So that means you will have to pick one of the lecturing slots for the second half, okay? Second half of the course, okay? But you also have to do the support role during the same semester. Now, all 6101 students, you guys are formally enrolled only for the half of the semester that you're doing 6101, but you're welcome to attend all of the sessions, okay? Now, external guests and 6101 students also are required to do a project, okay? This is so that you get some actual practice of some of the techniques. And now this is extremely easy because of GitHub, right? So there's a lot of source code out there for NLP, IR recommendation systems. So it's not hard to do a tiny project, okay? The hard part is finding data and tuning parameters, okay? So that 60 hours is up to you. I'm not going to check it, okay? It depends on how much time you have, okay? This is, again, based on what we know from 6101. So a 2-credit MC module in NUS is about 130 hours. So 60 hours amounts to 2 MCs. So that's the reason why we have this, okay? So we don't care about the particular type of project you do, but we'll talk about this a little bit more. You can do projects aligned to my group. You can do projects that are interesting to you. I mean, all projects should be interesting to you. And you can use it as a chance to connect with external participants, or, you know, if you're an external participant, connect with NUS staff as well as students. Okay, I think this is really one of the key reasons why we offer this as a public service too, is because we want to connect back to industry, we want to give back, and we want our students to benefit from having, you know, some linkage between parts, okay? So when it was pre-COVID era, we also had social activities, you know, to meet up and drink beer and what, but with COVID, we'll have to clink our glasses virtually. Sorry about that, but hopefully next time we'll have a chance to see each other in person, although, you know, in face-to-face, not through Zoom, okay? Now, I already went over this, but basically, again, the idea is that the lecturer is a facilitator. They're introducing the papers, and they may not do a particularly spectacular job at being factually accurate, and that's fine, okay? That's not the point, right? And hopefully having an interactive session rather than a lecture is going to be more helpful, okay? And support, again, means just complementing, okay? So what you need to do is, as a lecturer, by Tuesday of the week, when you're lecturing with your particular group, decide on, I'd say 2 to 3, okay, not 200 203, 2 to 3 core papers that you want to read. And then you can look with your support staff and find interesting extensions. This is very easy to do with Google Scholar. Just find papers that cited that paper that have an interesting name or subtitle to what you're doing. Then find presentations or slides on the web or video lectures. You can play a segment of a video lecture if you find that useful too. Okay. Then you have to coordinate the lecture. Okay, split the duties by papers or by sections. Okay. So hopefully each paper takes about 10 to 20 minutes of discussion, and it's fine if you get bogged down with basics, okay? But you guys can try with the lecturing crew to establish time limits which you want to hit all the parts, okay?
Yes, yes.
Again, we don't need to talk too much about the actual results. Many of the results are not very interesting. They just say we're better than state of the art or soda. But sometimes looking at the discussion and how other people view their work, meaning citation sentences that describe that work later on, can be helpful. Okay. And then for the purposes of YouTube and video lectures, it's helpful to have a larger cursor. So, or if you have mouse support or pen support on a stylus, you can do this so it's easier to follow. It's incredibly hard to scrub video without some support. I mean, if you've ever watched a video and you're trying to follow a tiny cursor, that's pretty terrible, okay? So you may want to try that, okay? So I've already gone over this, but basically the general channel is where you want to raise issues. So I hope you can do that even now, okay, on the general channel, raise your questions and things of that sort. And you'll need to update the README and the about and the markdown file on these two repos, okay? So the overall timeline for how a particular iteration works, okay, is on Tuesday, a paper list should be disseminated by the lecturing group on Slack, okay? Then on Friday, we actually have this reading group, okay? Then on the Monday afterwards, this is my responsibility. I'll go clip the YouTube video to make sure, the odds and ends are okay, okay? And if any of you have any objection to any of the footage, let me know, I will scrub it, okay? But again, this is made publicly live, so the edit will have gone out to replace the original video, but that means some people might have seen the original one, okay? And then T plus 7, meaning the next Friday, we'll have another reading group, but that means the Scribe, the support group, needs to finish compiling all of their notes, okay? And to put the
Yes,
PR in so that everything can go onto the website. Okay, so now what I'm going to ask you to do is go to your participants list in Zoom and then just tell me whether you understood or not. If you understood what I was talking about, please put up a check mark. I think maybe you can see it. I'm not sure whether you can. Okay, so Mingang says yes, Chenglei says yes. I want to see at least 50% yeses before we go on. Okay, this is just to make sure everyone's paying attention. Okay, and this practice you can also do on your own when you're lecturing, okay, is to make sure that people are paying attention and then we can go forward. So we have a couple people saying yes. I'd like to see a couple more. So, okay, I see Judith said yes, Alexandra said yes, Mingnang said yes, Mavavita said yes, Chenglei said yes, okay. Okay, very good. So we are going to use the participants list a little bit, and you can use it as well to make sure that everyone can follow, all right? So otherwise, most of our chats and discussions should be on Slack, okay? So here in Slack, I hope you will raise your questions here, okay, so that everyone can see what's to be discussed, okay? All right. So also in Slack, you will have noticed there are quite a lot of different channels here, and I want to tell you what they are. Okay. So we have our first year PhD students in NUS. They're all hopefully having a nice conversation with each other. It's a little bit hard to know each other, but I assure you, part of the benefit to studying in NUS is because you have a lot of other very, very smart people in Asia, all co-located in the same place. So this is one of the hopes that we have is to organize you into a coherent cohort of students, okay? Aside from that, there's also the project channel. So I hope many of you who are external guests who are going to continue with this and commit time to doing this will join our channel. You can join now if you haven't already. And I will talk about this towards the end of our first reading group session. So after all of the presentation about basic sequence to sequence work. Okay, and I'll brief you a bit about what the SOC term project showcase is about. All right, so so this is a good channel to join if you have that deliverable that I wrote about in the course, which is that all external participants, all 6101 students need to do an external project. Okay. Aside from that, you'll see over here that there are a list of different week preparation channels. So once you are assigned to a particular channel, you need to join these. Okay, I'll try to supervise and make sure everyone gets joined in. But basically, after the semester starts, there will be people assigned to different parts of the course, and you'll need to join the particular preparation channel to go over independently of me, but collectively as a group, the lecturing and support duties. Okay. All right. So one of the key documents that we need is this one. Okay, let me just get rid of this for now, and this one too. Okay, which is the lecture preference form. So for this reading group to work well, we have to distribute the duties. It's no good if everyone wants to do, for example, machine reading comprehension because it aligns with the projects that they're doing or their thesis, okay? So what we need is for people to tell us which lectures they're interested in, okay? So you have to, as an external participant, list one session that you're okay to do lecturing for, okay? It doesn't mean you need to know the material now, okay? It means that you're committed by that particular week to know the material, okay? This is a preference, okay? So if you have more than one preference, you can just comma separate them. Many people have put like 7 and 8 because that's one topic, they don't mind which week they're associated with. If you have a preference, let's say I want week 4, 5, or 6 and 7, just put a comma between those, okay? I will try my best to do that, okay? And then 1 week for the support role. Now, PhD students in my group have to do 2, okay? 1 for each, okay? So they need to write down, for example, something from week 3 to week recess for the first half, and then week 7 to week 13 for the second half, okay? I will be arbitrating. So you'll see that this column here in blue, you can't touch, okay? Those are protected columns. Those are the ones that I will assign. So once you see a number here, that means you are supposed to work on that. So for example, this week we have Tongyao and Zijin and Chenglei and Tianyang doing the presenter and support role, okay? And my job is basically just to balance, okay? So I have this sheet that just does counting, as you can see here, counting of the numbers that I've assigned. So our job is to make this as a uniform distribution as possible, okay? So once that's done and you see your name listed with a particular presenter role or support role for PhD students, you'll see both of these entries for 1 and 2, okay? Then those are the roles that you'll have to do, okay? If you have any questions, please unmute your mic or raise it on Slack. Either one is fine. Okay. No questions? Abdul Wahid, do you have any questions? Nope. Okay.
No, Professor.
So, yeah, go ahead.
No, no, sir, I don't have any question.
Okay. All right. How about anyone else? Anyone else have any questions about how this works? Okay. So I think you've all seen this page over here, right? This basically gives the idea of what we have decided for this semester to do. Okay. So we're going to cover mostly natural language processing work. We do have a little bit of work on conversational recommendation systems, but we could change these topics, but this is probably what we've decided at this point. Okay, so you can take a look at this set of things, or it's also in that particular worksheet if you saw it before. Okay, where is it? Did I throw it away already? I think so. Okay, but if you go back to the lecture choice worksheet, which is I think here, no. Okay, then you should be able to see that information about which types of topics are being discussed on which week. Okay, so you can take a look at this sheet first and say, oh, I'm sort of interested in domain adaptation. I wouldn't mind studying a little bit about that. Or I've read some papers in this area. I don't mind presenting a little bit more. Okay, so week 2 means slightly more advanced. Okay, not just the basic papers. Again, because the reading group is only 2 hours, we only have about an hour and a half to discuss. So it means that it will be less than 2 or 3 papers. So if you read more than 2 papers in an area, you are already qualified to do the week 2 type of presentation. Okay. All right. All right, so I also mentioned the support role. Okay, so the support role, basically you can go to this location, which if you look at the page, okay, there is a part where we describe where is this set of documents. Okay, so the scribing notes are here. Okay, bit.ly CS6101-2010. That's the semester 2020. Semester 1 is 10 notes. Okay, so if you click on this link, it will just bring you to that Google Drive page. Okay. And so how you do this Google Drive work is then, sorry, not this one, I'll fix that up, okay, is to actually, all right, come to this page, and when you're doing the support role, you can take this template document, okay, and just save a copy of it, okay? Somebody in the support group has to make a copy, okay, and then just start replacing all the things in here. So for this week, for example, I hope Tianyang and who else is Chenglei, okay, the 2 of you are assigned for week 2. We'll be taking notes on this, and those of you who are listening in, please feel free to help out, okay, so you can find this document. I'll put this document on Slack right now, and so you can see it, okay, yourself. I'll just write it. Okay, so you can go here and go ahead to modify that, so you can put on whatever you'd like there. Okay, so that's basically how the reading group works. So for the next hour or so, we're going to let Zijin and Tongyao take the floor. And then periodically, when you have questions or links, please ask. Again, this is not supposed to be a lecture. It's supposed to be a reading group. I know it's really hard to facilitate a virtual reading group. That's why we try our best. And I asked you to turn on your cameras, okay? Yeah, feel free to unmute, just chat. And if you feel more comfortable on Slack because it doesn't interrupt the lecture, you're welcome to do that, okay? So with that, I'm going to stop my screen share, and I'm going to ask you if you have any questions. If you have any questions, please raise them on the general channel. We are very friendly. We don't bite. So if you have any doubts or concerns, please ask. Okay. So again, we'll go for about an hour. And then after that, I will discuss a little bit in the last 30 minutes about projects, because I know some of you are wondering about that. Okay, so Zijin and Tongyao are 2 undergraduates, senior undergraduates at NUS. They've been working with my group for the last couple of months, and they have bravely, kindly volunteered, stepped into the ring to give the first part of the lecture. So Zijin and Tongyao, over to you.
Okay. Let me share my screen. Can you hear me?
Yes.
Okay.
Yes.
Good. Okay, let's start. Good afternoon. Welcome to the reading group. So this is the first session of the semester, and we just want to start with something simple. And we choose this topic of basic sequence-to-sequence learning. And we hope that through this session, you can understand the paradigms of doing sequence-to-sequence learning in a context of deep learning. So why do you want to choose this topic as a starting point? Here's a reason. There are a lot of tasks that can fit into this sequence-to-sequence model. So a sequence can be really anything. Can be a text, which is a sequence of words, can be a video, which is a sequence of images, and also audio. So there are many tasks that can be regarded as sequence-to-sequence learning. For example, machine translation, video description, speech recognition, and question answering. So let's take question answering, for example. It is essentially mapping a sequence of words representing the question to a sequence of words representing the answer. So it will be useful if we can develop a domain-independent method that learns to map sequence to sequence. And here is what motivates researchers in the area to develop such a framework with the help of deep learning. So today's agenda will be like this. We'll be focused on sequence-to-sequence learning applied in machine translation. We'll first start with the 2014 paper that introduces us the LSTM-based sequence-to-sequence model. And this is the first paper of doing sequence-to-sequence learning with deep learning. And next, we look at another structure of neural networks based on convolution. And eventually, we will also cover the very popular model these days, transformers, that use only attention to do sequence-to-sequence tasks. So Zijin will first discuss LSTM-based sequence-to-sequence learning.
Yes. So please look at this page. And so we start from the LSTM model because it's a basic Seq2Seq model. And before that, we were using the deep neural networks to do this kind of tasks. But the limitations of this method is that it's only applicable to problems whose inputs and targets can be sensibly encoded with vector of fixed dimensionality. However, the most important problems in machine translation or audio translation and similar stuffs are best expressed with sequences whose length is variant. For example, if you translate an English sentence to a French sentence, it could be very possible that they are of different lengths and different number of words. So it will be better if we can have a structure that can map an input sentence of variable length to a fixed dimensional vector representation. Next. And these are several attempts that that is mentioned in the paper about how to solve this Seq2Seq problem. And like, for example, they try to map the entire input sentence to the vector or use differentiable attention mechanism. And they also mentioned some paper raised solutions such as the connectionist sequence classification. Next. And so we will look at the straightforward structure of the LSTM. As you can see in this figure, we are trying to read an input sentence ABC and produce the WXYZ as output sequence. So the model stops making predictions after we output the EOS, the end of sentence token. And we need to note that although it's not reflected in this figure, in experiments, the LSTM actually raised the input sentence in reverse order, which means we will read the WN and WN-1 and so on. because this can have some advantages, such as introduce some short-term dependencies that help to improve the performance, and we will mention it later. And next page. So let's look at more details about the model. So here we try to calculate the conditional probability of this formula. So the x1.xt is the input sentence, and the y1.yt prime is our corresponding output sequence whose length is t prime. So here the t prime is not necessarily equal to t. And for this part, the V is a fixed dimensional representation of the input sentence. And here we got this from the first LSTM structure and it's given by the last hidden state. And then the LSTM will calculate the conditional probability given the input sentence as well as the predictions before the current word you are trying to predict. And we do that with the standard LSTM language model to predict the next word given the previous words. And so basically the idea is to summarize, the idea is to use one LSTM to raise the input sentence and another one to extract the output sequence from the vector V given by the hidden state of the LSTM. Do you have any questions? You can mention that.
Oh, Zijin and Tongyao, thanks for that introduction. So you said there's one LSTM and another LSTM, but in the diagram that's shown in your slides as well as in the paper, it looks like a single LSTM. Can you help us understand why there are two?
There's an encoder LSTM that reads in a sentence, ABC, and then encodes it into a hidden state. And then this hidden state will be passing to the decoder LSTM, which is doing generation of the target sentence. So in this case, we call it two LSTMs.
Is everyone clear about that? Do we want to discuss this point?
So can we have, instead of two encoder and decoder, can we have a single LSTM where the parameters are shared?
Anyone want to try to take that on? Is it possible to do it just in one single LSTM rather than two?
I think it might not be better because for encoder decoder, generally if used for text translation, the sentence syntax and the pattern of different language are different. So if you use the single LSTM, that one might be influenced by one of the languages. So I think there's maybe parameter sharing is not a good idea for the encoder and decoder.
Okay, so Tianyang said maybe it's good to have a separate encoder and decoder, and that's generally what we do. But you know, those are some of the considerations that we would make, right? So, for example, let me see what I can draw this, right? If you have this, let's see, does that work? Yeah. Okay, as a representation, right? Then you could feasibly translate to several different languages as output, right? And each of these would be a different decoder, right? So you can think of this W at the end as some type of interlingual knowledge representation of the sentence, right? That's one reason why we would try to split that up. Okay, but generally when you want to train things end to end, right, you want to optimize basically what happens at the very end, right? The translation quality. So it really doesn't matter how bad or good this thing is in the middle. It just happens to be the case that for a lot of NLP applications, that if you have a good intermediate representation, you can do a lot of different tasks with that representation. So we'll talk about that later. Okay, does that help? Anyone want more explanation? Dev?
I think what Tianyang was saying also was like when there is multiple languages, we might have to have joint vocabulary if we have parameter sharing. But if we segment, like if we have different encoders and decoders, we can have dedicated vocabularies, sizes, and the parameters would be more efficient in that sense.
Xiaochong also mentioned on the chat that GPT also uses a single decoder. So Xiaochong, can we invite you to elaborate?
Yes, can you hear me?
Yep.
Yes, I have heard the question whether we can use a single decoder to do the text generation tasks. Yes, GPT is a single decoder model using multi-layer transformers, and it's actually a language model which predicts the next word depends on the previous words, and so I think GPT is an example to answer the question. And also, rather than GPT, other modules like LSTM or CNNs, also we can build the models using multi-layers to do the text generation. It's the same meaning, I think.
Mm-hmm. So Jiaying also wrote a little bit on GPT-2, and so did Chenglei. So Chenglei, do you want to explain your comment?
Yeah, so I think if we're talking about GPT, so it's not really sequence to sequence, but rather just doing language model pre-training. And actually, I think like things like T5 would be more like sequence to sequence. Like yeah, so for language modeling, there isn't something like mapping from a source to a target, this kind of thing. It's just yeah, it's just learning a language model.
Okay, great. So yeah, let's continue. Again, if you guys are online and you don't have, if you have sufficient bandwidth, please do turn on your camera. It's easier for everyone to see each other. Okay, Tongyao and Zijin, please go ahead.
Question, is it
Yeah.
okay? Yeah,
Of
sure.
course.
So if you have two LSTMs, right? How do you train the decoder part? Because there is this intermediate things that, I mean, I can't imagine how you back propagate from the output from the decoder. So you decode, then you may get some kind of loss. So how do you back propagate the signal to the encoder part, right? If it's two separate networks, so how does it back propagate?
Anyone want to try to explain? If you know, it's okay if we don't know. Okay, I mean, Ming Liang is asking about training end to end, right? Because you obviously have to train the system. So how could you optimize when there's two different components?
I think it's because two components are connected through the through the hidden state. So it's not exactly that they are completely separate, but it's just after we pass the input through the encoder and then we pass through the decoder. So they are actually connected through intermediate hidden state. Yeah.
Okay. That's fair. Okay.
So we go to the next page.
Yeah, I think it's fine. Yeah, thanks.
Yeah. So here is the like just the mentioned before the training, like the training target of this LSTM model is to maximize this probability of given a source sentence S to predict the to get the correct translation T. And after the training is done, when we are inferencing the model, we will just retrieve the translation with the highest probability. Next. And here is some experiments that the paper did. One is English to French test. So given their inversed 5 deep LSTMs and left to right simple beam search decoder, they get a blue score of 34.8. Next. And another test is the next page. Another text is a statistical machine translation system. And as here we can see, they got a blue score of 36.5, which is improved the baseline system by 3.2. And these are the two tests I mentioned in the paper. Next page.
Which paper is that slide from? Is it the same paper, the sequence-to-sequence learning?
Yes, the same paper.
Okay, yeah. So when you read this paper, I think one of the things you guys should be looking at is what types of things that they change. So one of the things that they changed here is the beam size, right? And beam, of course, is very important for search, right? I mean, we know that from A-star search or other things that you might have learned in your AI courses or ML courses. But changing to a beam size of 1,000 is pretty large, right? So when they did that for the large one, they're not changing the beam size. Sorry, they're changing the best list, right? The amount of best results that they're putting through the lattice to choose for end result. So when you read these types of papers, you can think, okay, how much computation is involved in that? How much memory is necessary to carry out these types of experiments? Because you can see there's not that much of a change, right? Upwards. Actually, you can see what seemed to make the most difference was using the ensemble, right? Because the ensembles seem to make a big change in the performance. So thinking about these parts are critically important when you read research papers, because their architecture, design, and the engineering aspects that they report are obviously the ones that worked, right? There are plenty of things that they may have done that didn't work, that they didn't bother to report, or that the reviewers thought were not that useful and got excised. So you need to read all of the deep learning papers very carefully. Especially with respect to the size of the data set. So this is, MT14. So to know a little bit about the size of the data set and the amount that's being used for each language will tell you a lot more about whether that type of architecture is well suited for the task or not. So I advise my students all the time, don't look at the performance results. Look at the amount of data that you have. Look at how complicated that model can be given the data, right? From your machine learning courses, overfitting is a tremendous problem in deep learning, right? So if you choose a model that's in a paper from Facebook and you're from NUS, well, good luck, right? We don't have that many computational resources or data resources in NUS compared to FAIR. So these are not the types of experiments that are easy for us to execute. We want to execute experiments that are on the type of data that we have access to. So keep that in mind.
Okay, is there any question regarding this paper? Because we are going to jump to the next paper afterward.
Oh, I want to raise a discussion about the decoder encoder. So for encoder, let's say for text translation models, we use some language to train the S2S model, right? So say we use English to train the encoder, and then we use German to train the decoder. And then can we just use the same encoder, and maybe we use another model to train another French to Chinese for another model? Then can we match up the different encoder and decoders to make a translation between English and Chinese or French or German, like that?
I think that's one of the research topics in machine translation, about how you can apply different languages, like just have maybe one model that can translate across different languages, something like that, multilingual.
No, I mean, so we have two data sets. One is language A to language B, one is language C to D. And then after we train two models, can we match up? Can I just train the S2S model, we train the A to D? So we match a encoder to another decoder from another dataset. So in that case, the model still work.
Yeah,
Something like that, where you have different source languages and different target languages, and you have some interlingual in the middle. Is that right?
So initially, we only have A to D, B to E, and C to F. And then we built like 3 models. And can we just separate the encoder and decoder and do other measures?
So yeah, that has been tried before. It does work, not very well. And so what people have done is do joint tasks, okay, which has worked very well. If you look at a lot of the recent NLP papers, they show that a representation, especially like pre-trained language model, when fine-tuned appropriately, can handle multiple tasks. So the whole point is to try to form up some type of joint loss. Okay, some joint loss that can optimize the interlingual representation, that circle and rectangle representation in the middle that can be suited for many tasks. Then, even when you have trained on, let's say, representation of A, B, and C, and form this interlingua, you can pair it with a new task that you haven't seen before and not trained or done before, let's say G, that just comes and you can apply it directly. So of course, all of this can be done better with augmented data, but maybe not necessarily at the beginning. Okay, good question. Other questions, especially from external folks? Anyone want to raise anything?
Professor, can single encoder decoder can be used for multilingual translation like A to P, A to C, A to D?
So you're talking about an autoencoder?
Or can single encoder can be used for multilingual machine translation like A to P and A to C? Source language is same and target language may be different.
Yes, you can do that. I think that was what Tianyang asked, Abdul.
In that case, I
So
think
you can
like
do it
source.
just singly. Go ahead. Okay, Alexandra wrote on Slack. I think you can both all see it as well, right? To have a discussion about scoring. So maybe that would be a good session if you guys are interested. So if you are interested, just emote something on his message so that we can know whether we want to devote time to that. So I added a check mark to his message. So if we want to do that, we can maybe have one of the sessions also tuck into this part. Okay. All right, so Tongyao and Zijin, yeah, you can go ahead to the next paper.
Okay, so just now we look at the first attempt of doing deep learning-based sequence-to-sequence learning using LSTM. It seems pretty reasonable because traditionally LSTMs have been used for sequence modeling. So this is just like an extension. And now we are going to introduce a very different way of doing sequence-to-sequence learning based on convolution. So there's no recurrent structure at all in this network. And however, there's still the basic paradigm. So there's an encoder, which is given here, and there's a decoder and attention in the middle. So the main advantage of this model is that training is very fast. It's 9 times faster than the RNN-based method because in CNN, we don't have to wait for the previous output of the previous layer, and we can do a lot of computations in parallel. So we are going to take a look at the model structure of this model in detail. First, we look at this side of the encoder. So on the encoder side, like any NLP task, we first convert the word to the embeddings. And also something special about this network is that it adds a positional embedding into the word embedding. So the reason why we want to do this is because unlike LSTM, which automatically encodes the position information, the CNN needs some additional information about the position of a word in a sentence. So we add this in and get the final combined representation of each input. And then we look at the key idea of the network, which is doing convolution. And similar to what we see in image classification or any computer vision task, we have a sliding window like a kernel, and it slides through the sentence as shown by the blue triangles here. And it takes in k input elements, so k is the kernel size, embedded in d dimensions, and outputs a single output element with length 2d. And this output element has two parts. Let's name it A and B. And then just like any typical CNN network, we have convolution and followed by a nonlinear activation function. So here we use these gated linear units that calculates a nonlinear activation. So it decides which part of A are relevant. So if you look at this function, it's a pointwise multiplication, and this is the elements in A, and then B is passed through a gated sigmoid function. So this will be passed to the next step. And also, in order to allow for training of deeper networks, we add a residual connection directly from the input to the output without going through the convolutions. And the decoder side, we follow a similar structure. So as you can see here, we have a convolution and we have a gated linear unit, which serves as a nonlinear activation function. And what's kind of different is that because when we are doing the decoding, we are trying to predict the next word. So we have no access to information that is after the current word. So as you can see, the triangle on the encoder side is like this, but the triangles on the decoder side are facing one direction only. So after looking at the convolutions, we now look at another key design choice, which is attention. So in this model, we applied this thing called multi-step attention. So it's applied after each decoding layer. And how attention works is that first we get a decoder state summary. So for layer L and word I, we will first calculate its decoder state summary based on the decoder output from the previous time step, and then the embedding of the previous word, the previous predicted word, which is given here. And then we will calculate the attention score, which is a dot product with the encoder output. And and it's given by this formula here. Basically, the intuition is that with this attention, the model can extract the information from encoder outputs, that are relevant or aligned with the current decoder state. And then we calculate the conditional input, or we can call it a context vector, that is based on the encoder output as well as the attention score. And finally, we add this conditional input to the decoder layer, to the decoder hidden unit, and pass it to the next layer. And also notice that in this diagram, there's only one encoder and one decoder, and it looks very simple, but in the actual implementation, there are 20 layers of encoder and 20 layers in the decoder, which means that this attention is repeated 20 times, and also convolution is repeated 20 times. So it's a really huge and deep network. So when we see this model as a whole, we can realized some key design choices the authors made that allow it to work pretty well. So first, there are a lot of stacked convolutional layers, which allow for large receptive fields. So the kernel size of convolution in this case is only 3, but because we have stacked 20 layers, so as you can imagine, as the layers go deeper and deeper, the model extracts information from a larger neighborhood. And in addition, there's also multi-step attention. So this allows us to consider which words were focused on previously in the previous layer, because we have added the conditional input as a conditional input to the decoder state. So it gets passed through layer by layer. And overall, these two design choices, the stacked convolutional layers and multi-step attention, gives the model access to a lot of information when it makes a prediction. It has information about the word that was attended previously and also a large receptive field. And this CNN model is able to achieve a comparable Boolean score, which is the metric used in machine translation. It's slightly higher than RNN-based models, but the main advantage is that its training speed is much faster, because in CNN we don't have to wait for anything really. Like we can just like all these things can be computed in parallel, and it's just a lot faster than LSTM. So the model overall, it achieves good performance with much lower time consumption. So I guess I believe is 9 times faster than the LSTM based models. Yeah, so that's it for this model. Are there any questions?
I have a question regarding regarding your figure, like in the top products of the embeddings inside. What is the difference between the yellow and the blue color?
So this diagram is taken directly from the paper. It's just telling you which part of the encoder outputs that we are paying attention to. So remember we have this attention score. So we would so just intuitively we will compare this decoder output, which is from here, and then compare it with all the encoder outputs, and we will see which one aligns with the decoder output the most, so that we will pay more attention to it. So it's just a weight that we put to the encoder output, so that when making a prediction, our model knows which part of the encoder outputs that we should pay attention to.
Oh, okay. And for the convolution part, can we explain again, like how the shape of the triangle depicts the idea of direction?
Yeah, okay. So maybe I assume many of you already understand what is a convolution, like typically in a image classification task. So the idea here is very similar, but it's just not moving within a image, but within a sentence. So in this case, we have a convolutional kernel that is takes in k input elements embedded in d dimensions. So we have maybe many words in this sentence, and each of them would have a word embedding. So we have obtained the embedding previously. And then each of them have an embedding of d dimensions. We will take k such elements and just do a convolution. So they will have kernel and then output a single figure. And then we will have 2D of such convolutional kernels. So this will be our end result. So we will just move this convolutional kernel slowly towards the end of the sentence. So this is how convolution works in a sentence.
So one of the key things here is that when we have the input, right, for the encoder part, you can see the whole sentence, right? So you have the whole English sentence, start sentence, they agree, end sentence, right? So when you're encoding a specific word, like the word they, okay, you can see context to your left and to your right. That's no problem. Okay, so that's why the triangle is just like funnel shape. Okay, you get to look at the words to your left and the feature words to your right. Okay, but when you're predicting, right? So if you go to the next step, right? In the prediction part, when you're trying to generate a word, let's say this word here, you obviously can't see what's going on in the future because you haven't predicted it yet. Okay, so that's why the convolution here only allows you to look at the past predictions, what you've already generated. So in order to generate this S, right, we get to know that previously I had made the decision to generate two P tags, right, the start of paragraph tags, but I don't get to see that I wrote the German word I later on because I don't have access to that. I'm decoding. The decoding is sequential.
Oh, okay. That's very clear.
Okay, the other thing you asked about the attention part, you can see what it means. Okay, so this yellow, and this yellow is showing high activations for attention, right? So if you look at the first part, which is the P tag, okay, that's represented here, that means there's a start of sentence, and it's selecting from the decoder, okay, which of these four things here are most relevant, right? So it's basically looking at this column, right? And so we see that the P tag and the P tag in both the source and the target line up, right? The two yellow bricks in the middle basically say the word agree. Let me just change the color here. Okay, the word agree in English lines up with the two words the word they lines up with these other words, right? So there are three words in German and two words in English, right? And so I think, yeah, I got it wrong. The agree is lining up with the Simmons Z, right? And they is the C, yeah. And then the last one I think is the punctuation, right? The end of sentence. Okay, so it's just meant to graphically illustrate where there's high attention, like a heat map. Okay, other questions that we have from the floor? I think it's really important to get our basics right before we move to transformers. And so Chung had a question. Chung, do you want to ask by unmuting, or Rabio?
Oh, yeah. So can you we can move to the next slide? Let me see this slide. This slide. Yeah. So I see that when you're computing the attention score, you're using the DI. When you computing the conditional input, you're adding the EJs to ZJs, right? So EJs is a word embeddings. So my question is, why we're not adding this embeddings when we're computing the attentions, but we add it before we get the attentions and aggregate the attentions.
Anyone want to try that? So why do we have this conditional input? Why are we adding back the word embeddings?
I'm not sure, but is that maybe for some extra information that like maybe there are some information in the word embeddings that cannot be convoluted, so we keep the original embeddings.
Yeah, I agree. I guess it's more like when you are making a specific prediction, it helps when you have direct access to the input word. So let's say for the encoder output here, maybe the vectors on the encoder output side has been passed through many layers of convolution, and really the information have been diluted somehow. But if we want, we can add this input word embedding directly, so that when making prediction, it has a very point-wise information about what is the input word at that time step. Yeah.
Oh, I see. So why do we add this? Why don't we add this word embedding to the DI and compute the attentions? So the DI, if we add this term in the DI, would have the point-wise information. I think, is it better?
I have a suggestion about this. It could be. It reminds me a lot like residual connections, like that. In computer vision, we use this thing called residual connections. Yeah. Such that we can basically kind of allow training to happen a bit easier. So, yeah, I was thinking if this addition of the plus E there is actually more to help the training be easier, similar to the purpose of residual connections in computer vision, like ResNets and stuff.
Okay. Okay, thank you.
So there's also a side conversation going on chat, which is great. I appreciate that. So anyone who want to answer Shulin's question about decoding, is it done in parallel or is it done in sequence?
Okay, I can actually, beyond that question, I have another question. So actually I can answer his question first. So I think it's because it's the CNN, so it can handle the information for the output sequence in parallel. So it do not need to predict next words before after the first words have already predicted. So actually I have another question, that is how can this model handle the different length input? Because I saw that unlikely the recurrent network, it can show where to stop, but this model cannot show where to stop. So I think probably this is the reasons why it need to add the conditional input, but I'm not quite sure if there is a maximum limited of the length of the input and output or other limitation.
Yeah, I believe the authors did perform padding for the input side. So yeah, it's because the convolution needs to move it through, so they have some kind of padding on the input side. But I'm not sure how really like handle, as you mentioned, the case.
So this decoding process will be like the transformer. It's just parallel, or we just predict same length sentence for each decoding.
I don't think they do decoding in parallel, because you need to have access to the word you predicted previously. So like when you are trying to do a decoder state summary here, you need to have the decoder output from the previous unit and also the embedding of the previous word that we predicted. So let's say we are trying to predict Steeman here, this word. Then we need to have the word embedding for psi. So it's still done step by step. So it's just like the transformers, you have to have some information about what you have predicted.
Okay.
Actually, I don't think this is the in a parallel. So I know what you mean. So you think the next word embedding is contain the information for the words before it. So but the decoder is prepared before before handling the information from the encoder. So I think it's kind of parallel process.
I think, so I know what happens in transformers, so I assume it will be the same here. Yeah, the decoding is different in training phase and testing phase. So in training phase, you have access to the ground truth, which is the correct output. So what you do is you do something called teacher forcing, which is you shift each word by one position, and then you can do the decoding in parallel for all the words. But in testing, you do not have access to the ground truth. So you would do it, you need to do it one by one, which is called an autoregressive decoding. So I think it should be similar here too.
Can anyone please address the case of like long-term dependency when you do parallel computation? Okay, can you hear me?
Can you say it again? Because your background is a little noisy as well.
Can you please explain the case that for sequence-to-sequence model, we need to have the long-term dependency. Now, if we do parallel computation, how that works in practice, like our long-term dependency, how you get that information?
So yeah, long-term dependency is not handled particularly well in any of these architectures, right? So LSTM, you have the RNN model trying to model dependencies, but the problem is that, of course, it is only able to really encode the last couple of states. With CNN, again, you have a limited window because your kernel size is fixed. So it depends on the width of those triangles that you see in there. So they're not completely able to take in all the information. When we get to transformers, of course, you get to see the whole sequence in parallel. So you can take a look at that in a couple minutes time.
I guess the way the model handles long-term dependency is through the stack of layers. So let's say if we have many layers, then as you can imagine, we will have something like this. So the input length will be shorter and shorter, and also because we have attention in between each of the steps. So let's say if we are trying to predict a word at the end, maybe it will search through this layer and then goes from, because the attention is embedded with all these layers. So it learns to attend maybe to the previous word, which one, and then also learns to attend a word at the previous layer. So it's like a stacked CNN, and with attention, it handles long-term dependency in this way, I guess.
Okay, Henchan also mentioned a little bit about length of sentences. So in section 5.3, they do talk about how they deal with sentences of different batches, right? So they do the inference with batches of the same sentence to make it easier. So I'll paste that into Slack. I know we have conversations in 2 different places, and that's great, but it is also a little bit difficult to keep track of what's going on. So it may be good for us to try to just use Slack, because Slack allows you to actually paste images and other things instead of just in the chat. So where possible, try to use the Slack channel. Go ahead. All right, so I think we should probably move on since it's 2:21. So let's try to hit the hardest paper, or the one that's most popular, which is the transformers paper.
So I will try to demonstrate a simple structure, simply demonstrate the structure of the transformer model. So here, this is in the paper, attention is all you need. So here we use attention mechanism to develop the transformers instead of RN or CN. So here, for example, you are having an input and output, that's language translation. So there are two sections in this structure, which is encoder and decoder, similar to the previous ones. And next page. So to more deeply look at the structure, we have 6 encoder layers and also 6 decoder layers. And next page. In each encoder layer, we have the self-attention and the feed-forward layers in each encoder. So we have 6 encoder, and every encoder will have this structure. And in the decoder, we will have the self-attention layer and the encoder-decoder attention layer, and also the feed-forward layer. So here is a more complete structure of the transformer. So we have the fully connected feed-forward networks here. As you can see, the blue, the graph is drawn, the block is drawn by blue color. And the input embeddings, before they are put into the encoder, we will go through one layer of the positional encoding. So for this positional encoding, we sometimes use the sign functions. Like this is to kind of note the location of each word in this sentence to add its position. And we can also try to use other functions or the sign functions of different frequency. And then we go through the encoder to have the self-attention and also the feed-forward part. And we'll go through the layer normalization before output the probability. And next page. So here we allow the model to attend the information from different representation subspaces as noted in the figure. And this helps to solve the issue of the long-term dependencies. Next page. So here we try to compare the different complexity per layer of the different layers. And as indicated in the graph, that's a basic introduction of the transformer. So we didn't list the specific structure here, but we can discuss about it if you have anything to add on.
Can you please go back to the key, query, and value slide where we see the multi-attention? Yes, thanks. So I always have this confusion that what is key, what is query, what is value, like for encoder and also for decoder. Yeah, can you please give some insight that what should be my key, query, and value for encoder? I know that like for query and key, for like there is something changes in encoder and decoder level.
Anyone want to take that up? So there's a useful part of the illustrated transformer post that Brian put up. So you can read that part. It's sort of like about a third of the way down. It mentions what are the key query and value vectors, right? So you could take a look at that part. I will paste screenshot of that into the Slack in case you're interested to take a look. Anyone want to try to explain what's going on for that part, the key value inquiry?
If I remember correctly, in encoder and decoder, they are self-attention. So for self-attention, the query key value are the same thing, basically the output from the previous layer. So it's really called self-attention because you are doing dot product between Q and K, which is referring to the same thing, which is your previous layer's output. And then you do a softmax, then you multiply with the V, which is also your previous output. But for the encoder decoders, cross attention is a different thing because in this case, your query is actually the decoder's output, and then you are doing a dot product with your key, which is now your decoder's output. So you're doing a dot product between your encoder and decoder's output, and you do a softmax to get this kind of attention. So this kind of attention actually tells you like which part of the encoder is important for the decoding. So then you use this attention weight to multiply by your V, which is now your decoder's output. So in this way, you for this kind of cross attention, it tells you like for the current decoding step, which of the encoding step are more important. So yeah, so in summary, that just two types of attention. One is self-attention. For self-attention, QKV are the same thing, which is your previous layer's output. And such self-attention exists in the encoder and also the decoder. And another type of attention is cross-attention, which is between your encoder and decoder. And for this kind of cross-attention, your query comes from your encoder and key and V comes from your decoder.
I think you said it the opposite way, right? The query comes from decoder and key and value comes from encoder. Or is it?
You are correct, I guess, yes. Query comes from a decoder and key and value comes from encoder.
Okay, Jiaying also wrote in chat, if you are looking at the chat a little bit about, multi-head attention. So this is a part that a lot of people get caught up on. So maybe you guys can try to explain and we can all help out to explain what multi-head attention is doing.
I think the multi-head attention is kind of the combination of self-attention. So the different, like the multi-head, for example, each head attention has like different part that they think would be important to the features. So the subspace could mean they focus on different syntax and semantic, that they focus on different parts of the language, and then they try to get different information from each attention part and try to combine them together.
Anyone want to elaborate?
So by saying that, maybe you mean that they focus on the same like batch of tokens, but they just focus on different patterns or different perspectives about that certain batch of tokens.
Yeah, I think.
I'd like to think of it as, that there are different properties of words that are useful at different time points in parsing the sentence. So for example, in one part of the sentence, it may be very important to have agreement. For example, like when you resolve a pronoun, like it or the company, which one is it referring to? In another part of the sentence, you might need agreement for gender, especially in Romance languages. So you need to know that something is female or male now. Okay, there are other things where you need inference. So the problem with a single head attention is you only get one representation. You have to choose the best representation for the task. Okay, multi-head attention basically says, well, you get 8 different ways to represent what you're looking at, or however many heads you have. Okay, so you can store different types of information, right? So when you actually do the decoding later on, your decoder can say, oh, well, actually, you know, for this particular position, I really need to know, you know, what that pronoun refers to, or, you know, what the agreement is for this verb, which tense it's supposed to be. And the multi-head attention allows that, because you don't have a fixed single representation for each part of the input. You have multiple representations. So
Okay,
they
so
don't
in this way,
necessarily line up
sorry.
to a particular semantic. So I mean, I'm stretching the analogy, I think, a bit too far to say that, you know, there's one head for gender and there's one head for other information. In fact, in this paper, I think they tell you a little bit what the heads are actually paying attention to. But yeah, we can talk about that later. Yeah, Jian, go ahead.
Okay, so in this way, can we use techniques similar to dropout, and then we can choose the parts that best represent the tokens?
Rabio, you want to say something?
Yes. So how do you force a multi-head? Let's say I have 6 sets and they're attending to 6 times. But how do I force that one head will attend some important parts of the sentence, and other head will attend another important part? And so while compute time, how do I force this that not two of them will attend the same position or same thing? So how this works in practice, like 6 heads, but they're attending several things. But yeah.
Yeah, so I think the whole point is with neural networks, we don't actually care what they're actually representing, as long as they do a good job of the task. That's the point of end-to-end, right? So we're not doing any forcing here. We're letting the math take over and look for statistics. Now, of course, there are lots of people who say, well, you know, these transformers, they're actually smart. They actually encode certain things. Okay, smart should be taken with a huge dose of salt, right? Because it's just smart in the sense of being optimized for the task. Now, there are plenty of people in NLP who would like to see more real semantics being involved, right? So they'll say, okay, I want to force an attention head to pay attention to certain things, right? By changing loss function for that particular head. I think the verdict is still out on that. I mean, if you look at some of the papers, maybe we'll talk about it next week, about what the attention heads actually find, you'll see many of them are just positional in nature, but some of them have longer term dependencies. Does that answer your question?
Yeah, so it lands on its own, so I understand.
Yeah. So a lot of neural network architectures are like that. We don't actually know what they're doing, right? Even with our word embeddings, we don't really know what they're doing. We're just saying, you know, optimize for some criteria and then hope for the best, right? So even in the pre-trained language models, you're pre-training them for a particular task, right? For representing or predicting words that are missing, or net sentence prediction, etc. And we're not really saying that this is a real semantic representation at all. We're just saying that this representation is optimized to do the prediction for a particular task. So when you train a transformer, it's doing that as well. It's saying, well, you know, I give it, you know, multi-head, you know, whatever that is number, like say 6 degrees of freedom to represent your input at different parts. Okay, and then from those 6 degrees of freedom, I can choose the representation that's most suited for predicting this particular spot.
Thanks, that's clear.
Prof, if I want, I'd like to add something here. So I think with the degrees of freedom, we also get the trade-off of having redundancies. So the moment we are not applying any constraints on the heads, then the network might learn the same thing, which is what we see in some papers where they try to prune some of the heads away and the performance is still the same. And it leads to improvement in efficiency because there are lesser computations. So I think, yeah, it's a trade-off between the amount of compute power you need to learn different stuff versus whether it's learning or not, or it's just learning redundant stuff. So yeah, in redundancy, I think then the dropout point might be, which Jane pointed out, then it might have some implications there to combat redundancy between heads. How can we use dropout?
Yeah, Dev made a really good point about considering the efficiency of the inference structure when you want to prune heads off. Hey, let's go on.
I think so. To summarize our this reading passage, this reading group, we are doing mainly the 3 topics, which is the LSTM-based Seq2Seq model that so it's kind of remove the limitation of the previous deep neural network and trying to like deal better with the input of different size of different lengths. And then we do the convolutional Seq2Seq model that like try to use some computer vision related convolution knowledge to help with the prediction. And then it's the transformers structure that use attention, both self-attention and multi-head attention to improve the algorithm. And for the next page, we also included some other related papers that are also trying to solve problems using the Seq2Seq model. And if you're interested, we can discuss more about that later. Yeah, that's all for our presentation.
Okay, so let us thank the whole team. You can do that in whichever way you want. You could annotate their screen, you could clap, or you can emote. But yeah, please give them a round of applause for all of their hard work.
Okay. Thanks. It was great to join here and learn some interesting stuff. I really enjoyed it.
Yeah, so everyone will get a chance. So this is why we do it this way. Okay, we want everyone to give back to basic understanding of what's now current NLP architectures. And so I hope you will all do this work together so that we can all benefit. All right, so just for those of you who may have joined late, again, this is an open reading group, so anyone is able to join. I hope you will invite others from your respective institutions if they're not around today to join. But it does require help from you. So I'll take the screen back when you're ready.
Okay.
Okay, very good. To just mention a couple things again. So you'll just have to bear with me as I switch up. Okay, so again, the most important thing is that you come to this worksheet, okay, and you put your numbers down here. So especially for our new NUS PhD students, especially the ones that are doing it for the first round. So that's Zijin and Kathy. The two of you have put down your preferences, which are good. But especially for the other guests, some of you have already put your names in, that's good. Put your interests down so that I can help arbitrate. So I will try to run that NP complete problem to assign people to their appropriate slots, okay? And then you'll have to bear with me. Of course, we want to make sure that the upcoming weeks are stable. So those of you who are assigned to week 4 or week 3 will need to work very closely very soon. And again, to do that, you need to go to our Slack group. Where is it? Okay. And then join the respective channels. Okay, so there's a channel for W3. I've already started populating people in the groups that I know for W3 and also for W4. So generally, again, you need to, if you're working in W3, you will need to fix the papers that you guys want to discuss, again, 2 or 3 papers by next Tuesday. And those of you who are scribing for week 2, I think that was Tianyang and Chenglei. You guys have another week to get things done. Of course, it's always nice as this semester is still young, you're not too busy, you can get those things out of the way early. Okay, so even though you express preferences on the form, of course, that doesn't oblige me to select that for you for that topic. So if you get something that wasn't your cup of tea, you can join the particular prep channel for another group that you want and see whether somebody from there would prefer to switch with you. Okay, this reading group only works when everyone actually does what they say. So if you're an external participant, please don't bow out after you've listened to the talks. Do try to contribute. You learn a lot more when you actually contribute to try to teach or to clear up misunderstandings. Okay, so I will put this down over the next week or so. So you just keep an eye out on that. Keep an eye on Slack to make sure that the assignments are clear. Okay, we often have the case where external participants, because of course you're not obligated by me, I don't have any ways of collaring you, they disappear after middle of the semester. So we hope that you will try to stay the course and do the assigned work so that everyone can benefit. Otherwise, it's crickets all the way towards the end of the course. Okay, that's no good for anyone. All right, the last thing I want to do is talk about projects. So there is a component, like I said, in this course, reading group, I should say, that requires that 6101 students, so that means everyone here, okay, has to do a project. Okay, this is to satisfy the 2MC's worth. Okay, now that project can be really, really simple. It doesn't have to be complex. Or if you wanted to do a more complex one, again, I would say it's good to do it with others. A project alone is fine, but it's much more fun if you do it with someone you don't know. Okay, especially if you care to try to work with somebody outside of NUS if you're internal, or work with somebody inside NUS if you're external. Okay, that makes the community more well-knit and you get a lot more benefit of networking outside of your immediate vicinity. Okay, to be honest, because we're in COVID-19, your immediate vicinity is your home, right? You should be social distancing. Okay, so what does the project do? You can do any project you want, but there are some guidelines that are on the Slack channel, okay, for projects. Okay, so I'm gonna turn this here. And so you can see some of the projects that have happened before, okay, which is, you can see here like convnets from particle evolution or sentiment analysis using NLP, okay. So you can scroll through this channel and look at other things. You can also, in some cases, do a homework assignment for another course. So a couple semesters ago, you can see this was last year, we had an unsupervised reinforcement learning problem course, the one from UC Berkeley, we ran it here. So people did the homework assignments for that course. That's fine too, okay? Anything that puts you in touch with code and puts you in touch with data analysis is good. Okay, now those of you in Wing, of course, you're not obligated to do so, but if you find interest, you can do that. Now, we do have a number of PhD students in my group who may be willing to at least tell you about things that they're interested in. They're usually too busy, as I'm sure most of you are, to actually supervise other folks. But if you are working on a project that's of interest to other people, of course, you can talk with them and get advisements from them, okay? So my advice to most students in 6101 is find other project partners. It can be a project of size 4 or 5. All you need to do is take down a particular homework assignment or a particular data set or a particular GitHub code, run the code on a new data, okay? And most importantly is not the results, okay? It's your understanding of why the results are the way they are. Okay, that's key. I don't care about soda, state of the art, okay? I want to know why something works the way it does, okay? Why when you change a particular parameter, let's say number of attention heads or positional encoding method or self-attention mechanism, why it changes the results the way it does. That is to give you insight over the math. The math itself doesn't help anyone, okay? How you construct the math based on what you see in the data matters. Okay, so that is the key part of the project. You can take an existing piece of code, run it, get some results, try something else, and before you try it, make a hypothesis. Okay, this is very key to being a scientist. I've told this to all of my group members. We run experiments to validate what we think. Because we are scientists, we make hypotheses. Okay, we don't run experiments to find out why things happen. That's wrong. That's what we do when we don't know what we're doing. We just try, okay? Any machine learning system can do that. That's called auto ML, okay? We don't need humans to do that. We need humans to think, okay? So the important part is, well, you're studying for a PhD or any other type of work outside, okay? Is you need to develop your intuition, okay? No neural network has that currently, okay? Is, well, maybe they do, encode it, but they don't realize it, right? And similar for us, but develop the capability to understand why results should be the way they are and explain why they're not when there's some surprise. Okay, so that is the key part of the project. This is the reason why we have this lab rotation course for you. Okay, and this is the reason why we want you to network with people outside, because outsiders in industry often have very different perspectives that can help you a lot. And I think for many of the returning champions, as I like to call them, who have been in industry and keep on coming back to the course, even though we do different topics, is because they appreciate that connection. Okay, so I hope for all of our wing students as well as our 6101 first year students, you will make that connection, okay? It's extremely hard to do under COVID-19. I apologize for that, but there's really a global problem. And in Singapore, we're already very lucky. So I urge you to use this to your competitive advantage rather than complain that you have a disadvantage, okay? It really depends on your mindset, okay? So we're giving you a platform to do it. So let's use it to the best that we can. Okay, so you may be wondering why we do all these projects anyways. Okay, so I will tell you a little bit. Okay, so when you come up with a project title, you can write it down here. Okay, it doesn't have to be anything fancy. You can just choose homework assignment free from a course, or you can just give some fancy title. Okay, it doesn't have to actually be what it's not binding, okay? You can do what you want, but make sure that everyone in your team, if you have a team of students, has the same project title so we can color code it appropriately, okay? And one thing that happens in SOC every semester, okay, and you are invited, is steps. So just try to raise this up. Let's see what it works. Okay, it's loading. Okay. So every year we have, well, so I should say every semester, we have a project showcase. So here's one. Okay. So the project showcase is where we ask all the students who are doing project related coursework to show up and give some discussion of what they're doing. So for example, in our machine learning course, we do different types of projects related to machine learning. Okay, but for 6101, for example, I think 2 semesters ago, we had our deep unsupervised learning course. And basically, these are the types of projects that people turned in. Okay, so there's about 6 different projects from the cohort. Okay, so these are all, again, just a chance for you to come up, do a project, and, let's click through one of them, whatever. Okay, and then come up with a poster or some presentation of it so that we can show it off to the general public. So for example, this was a CycleGAN project, and I think they produced a poster. Oh, they didn't produce a poster, but there are some that have posters and videos associated with them. Okay, so this is the type of output we hope that you'll do. And if it is COVID-19 dies down, you will have a chance to come down to the School of Computing and give your project if you're local. If it isn't, then of course we'll have it virtually. So I think they're building some type of meeting space where you can exhibit your posters and talk with other people who are like-minded. Okay, this is a pretty big event. So you can see here about 1,400 people came to this particular event. Many of them are very interested in learning. So you know, we have some software engineering projects. I already showed you the deep learning projects and the machine learning projects. So we hope you'll partake as part of that. Okay, so that is the goal that we want you to do as part of the projects. Hey, if you have any questions, you can let me know. Basically, what we hope is by week 5 or 6, especially if you're an external participant or you're in 6101 locally for the first semester, you will have a notional project title. Okay, and there'll be some instructions about how to enter that into the STEP system. So you'll be given credentials to come to this particular website, okay, and then to you know, start putting up your assets for presentation. Okay, I don't have anything else for you today. I think it was quite a successful session. So I want to first, again, thank Tongyao, Zijin, and our support crew of Chenglei and Tianyang for fielding all of the questions and everything of that sort. And so let's give them a round of applause again. Okay. And so what you'll see is nothing for the next week until around Tuesday, when the recording is up and all of the other outputs from the Scribe group are up. You should see our homepage updated. So you should see, instead of this boring line here, you should see something that looks a little bit like this. Okay, so there'll be a YouTube video and then information about the slides and the references. So we hope we can build all of this in for you by next Friday. Okay, so with that, we've come to the end of the reading group. If you have any questions, I will still be on Slack for a while. But otherwise, I bid you a fond farewell and we'll see you next week. Bye, everyone.